In the present lecture, I will discuss the degeneracy in linear programming problems. The phenomenon of obtaining a degenerate basic feasible solution in a linear programming problems is known as degeneracy. Degeneracy in linear programming problems may arise in two stages. First one is at the initial stages. Second one is at any subsequent iteration stage. First we have to look for at the initial stages. At least one of the basic variables should be 0 in the initial basic feasible solution is called as the degeneracy in linear programming problems. Second one is at any iteration of the simplex method, more than one variable is eligible to leave the basis and hence the next simplex iteration produces a degenerate solution, which means time for minimum ratio of xp divided by coefficient of incoming variable is more than for the two variables. Next we have to look for the methods to resolve the degeneracy. The following systematic procedure can be utilized to avoid cycling due to degeneracy in linear programming problems. First step is find out the rows for which the minimum non-negative ratio is the same. First we have to look for which rows having the type for the minimum ratio of xp divided by coefficient of the incoming variable. Second step is now rearrange the columns of the usual simplex table so that the columns forming the original unit matrix come first in proper order. Third step is find the minimum of the ratio only for the tied rows, that is minimum ratio is the elements of the first column of the unit matrix divided by corresponding elements of the key column. If any row has the minimum ratio, then this row will be the key row. If this minimum ratio is also not unique, then we have to go for the next step. Next step is now find the minimum of the ratio only for the tie rows. Here minimum ratio is the elements of the second column of the unit matrix divided by corresponding elements of the key column. If any row has the minimum ratio, then this row will be the key row. If this minimum ratio is also not unique, then go to the next step. Next step also find the minimum ratio, but here we have to take the minimum ratio is the elements of the third column of the unit matrix divided by corresponding elements of the key column. So the above this step is repeated till the minimum ratio is obtained so as to resolve the degeneracy. After the resolution of this type, simplex method is applied to obtain the optimal solution. Here minimum ratio is the elements of the third column of the unit matrix divided by corresponding elements of the key column. Now we will discuss one example problem for degeneracy in LPP. Let's see the problem. Maximize z equal to 3x1 plus 9x2 subject to the constraints x1 plus 4x2 less than or equal to 8, x1 plus 2x2 less than or equal to 4 and x1 comma x2 greater than or equal to 0. Let's see the solution. First step is convert the inequality of the constraint into an equation by introducing the slack variables s1 comma s2. First we have to introduce the first slack variable S1 in the first constraint. Similarly, next we have to introduce the second slack variable, that is S2 in the second constraints. Now constraints are x1 plus 4x2 plus s1 equal to 8, x1 plus 2x2 plus s2 equal to 4, and x1, x2, s1, s2 are the greater than or equal to 0. Next, to rewrite the objective function in the terms of the x1, x2 and s1, s2. Now objective function. Second step is find the initial basic feasible solution. For this one, we have to consider the decision variables are the 0, that is x1, x2 are equal to the 0, and we have to introduce these x1 and x2 values in the constraint equation. We will get the s1 and s2 values. Here s1 value is the 8 and s2 value is the 4. Next step is construct the initial simplex table. So this is the initial simplex table. Here basic variables are the s1 and s2 and its cost coefficients are the 0 for the s1 and similarly 0 for the s2. And xb is the initial basic feasible solution, and we are obtaining the s1 and s2 values are the 8 and 4. And Cj is the cost coefficients for the decision variables as well as the slack variables. For this one, I have to observe the objective function. Here x1 cost coefficient is the 3, x2 cost coefficient is the 9, s1 cost coefficient is the 0 and s2 cost coefficient is the 0. Next step is calculate the Zj minus Cj values and to check the basic feasible solution for the optimality. If all the Zj minus Cj values are the positive values, that is greater than or equal to 0, then optimal solution is obtained. If at least one Zj minus Cj value is negative, then we have to indicate it by arrow, and respected column we are calling as the key column. If more than one Zj minus Cj value is the negative values, then we have to choose the most negative of them, and respected column we are calling as the key column. So first we have to calculate the Zj minus Cj values for the first variable, that is the x1. So z1 minus c1 for the x1 variable will become the 0 into 1 plus 0 into 1 minus 3. This value is the minus 3. Next to z2 minus c2 for the second variable, that is 0 into 4 plus 0 into 2 minus 9. This value is the minus 9. Next z3 minus c3 for the third variable, that is the for the s1, 0 into 1 plus 0 into 0 and minus 0. This value is the 0. Next z4 minus c4 for the fourth variable, that is the s2. So it is the 0 into 0 plus 0 into 1 minus 0. This value is the 0. Here observe the more than one variable having the negative value of the Zj minus Cj. Then among these values you have to choose the most negative value. Here most negative value is the minus 9 for the x2 column. So x2 column is the key column, and respected variable, that is the x2 variable we are calling as the enter into the basis. Next we have to calculate the minimum ratio, that is xb divided by coefficient of incoming variable. First we have to calculate for the first row. Here xb value is the 8 and its coefficient of incoming variable is the 4. So minimum ratio will become the 8 by 4, that is the 2. Next we have to calculate for the second row. Here xb value is the 4 and coefficient of incoming variable is the 2. Now minimum ratio will become the 2. So here observe the both variables s1 and s2 having the same minimum ratio, that is the 2, and both variables s1 and s2 are the eligible to leave the basis. So there is a tie among the ratios in rows of S1 and S2. This causes the problem of degeneracy. Now we resolve this degeneracy by applying the standard procedure. That is, find the minimum ratio only for the tie rows. Here tie rows are the S1 and S2. For S1 and S2 rows, we have to determine the minimum ratio. That minimum ratio is the elements of first column of unit matrix divided by corresponding elements of the key column. Here observe the S1 and S2 are forming the unit matrix, and the first column of unit matrix is the S1 column. So minimum ratio for the tie rows is S1 divided by key column elements. So first we have to calculate this ratio S1 divided by key column elements for the first row, S1 row. So here for the S1 row, S1 element is the 1 and the key column element is the 4. Then ratio will become the 1 by 4. Similarly, we have to calculate for the second row, that is the S2 row. For the S2 row, S1 value is the 0 and the key column element is the 2. So 0 by 2 it will become the 0. So among these two ratios, minimum value is the 0 for the S2 row. So this S2 row we are calling as the key row, and this row we are calling as the outgoing vector, and S2 variable we are calling as the outgoing variable. So S2 variable is the leave the basis. Next we have to identify the common element in the key row and the key column. Here key row is the S2 row and key column is the X2 column. So for the S2 row and X2 column, common element is the 2. So this 2 value we are calling as the key element. Next step is construct new simplex table by entering incoming variable. Here X2 is incoming variable and S2 is outgoing variable. So replace the S2 with X2 in the new simplex table. So in the basis we have to write down the S1 and X2, and CB is its cost coefficients, that is the 0 for the S1 and 9 for the X2. Next we have to do the following row operations, that is R2 new equal to R2 volt divided by key element. Here key element is the 2, and another row operation is the R1 new equal to R1 volt minus 4 R2 new. Here R1 volt and R2 volt are the row 1 and row 2 for the volt table, and R1 new R2 new are the row 1 and row 2 for the new simplex table. So first we have to do the first row operation, that is R2 new equal to R2 volt divided by key element. Here key element is the 2. Then R2 volt elements are the 4, 1, 2, 0, 1 and divided by 2. Then R2 new will become the, so 4 by 2 2, 1 by 2 is the 1 by 2, 2 by 2 1 and 0 by 2 0 and 1 by 2 is the 1 by 2. Then have to enter these R2 values in the new table. Similarly, next we have to do the another row operation, that is R1 new equal to R1 volt minus 4 times of the R2 new. First we have to write down the R1 volt elements. R1 volt elements are the 8, 1, 4, 1, 0 and R2 new elements are the 2, 1 by 2, 1, 0 and 1 by 2. Next we have to do the, so 4 times of the R2 new, that is 4 into 2, 8. So 1 by 2 into 4, 2, 1 into 4, 4, 0 into 4, 0 and 1 by 2 into 4, it is the 2. Next we have to do the subtract of the R1 volt minus 4 times of the R2 new, that is 8 minus 8, 0, 1 minus 2 minus 1, 4 minus 4 0, 1 minus 0 1, 0 minus 2 it is the minus 2. Then these values have to enter in the R1 new. So next we have to calculate the Zj minus Cj values. First we have to calculate the Z1 minus C1 for the first variable, that is the for x1 variable. It is the 0 into minus 1 plus 9 into 1 by 2 minus 3. It will become the 3 by 2. Next to Z2 minus C2 for the second variable, that is the x2. So Z2 minus C2 for the x2 variable is the 0 into 0 plus 9 into 1 minus 9. This value is the 0. Next one is the Z3 minus C3 for the third variable, that is for the S1. It is the 0 into 1 plus 9 into 0 minus 0. This value is 0. And last one is the Z4 minus C4 for the fourth variable. For the S2 it is the 0 into, sorry here minus 2, 0 into minus 2 plus 9 into 1 by 2 minus 0. This value will become the 9 by 2. Here observe the Zj minus Cj values are the 3 by 2, 0, 0 and 9 by 2. So here all the Zj minus Cj values are the greater than or equal to 0. Then optimal solution is obtained. Here all Zj minus Cj values are the positive. Hence the optimal solution is obtained. Then optimal basic feasible solution is, for this one observe the basic variables. So here there is the no x1, so x1 value is the 0 and x2 value is the, xb value is the basic feasible solution, that is the x2 equal to 2. Then we have to substitute these x1 and x2 values in the objective function. Our objective function is maximize z equal to 3x1 plus 9x2. Then substitute x1 value and x2 value. Then we will get the maximize z equal to 18. So this is the solution, and thank you.